Hello. My name's Caroline Payson. I'm Director of Education here at Cooper Hewitt, and I'm really excited to be welcoming you all here. You are our first public program since we opened on December 12th. Since we opened on December 12th, we've had over 30,000 people attend, which is thrilling for us, and opportunity to visit all of our exhibitions and play designer and interact with our digital tables and experiences. And we've been really excited about how wonderful people have felt about coming and the great press that we've had. And the next step, of course, is to start running programs to support all those wonderful new exhibitions. And this is the first one. So thank you all for coming and helping us celebrate our opening for a little bit more than a month. One of the things we'd also like you to remember, since we're now opened, is that we'll be doing a variety of public programs, some about the exhibition's tools, which is featured tonight, but also some will focus on beautiful users next week. We're also doing a series about Latino designers that begins next week as well. So please go to cooperhewitt.org. There's probably at least a program a week, as well as free programs for families, teens, and kids. And we would love you to tell everybody you know that we're now open and we're ready to have visitors not only in the museum, but for all of our programs. It is also my pleasure tonight to introduce our moderator, Matilda McQuaid, who is our Deputy Curatorial Director, Head of Textiles, and who, along with Kara McCarty, is one of our two curators of the exhibition tools. Oh, one more thing, sorry. You can tell we're new, we're not back. We're new to this, so I keep forgetting things. For those of you who want to tweet about this or who have Instagram accounts, our wireless access code is posted around the room, and our hashtag is extending our reach. Tools extending, sorry, hashtag tools extending. By the time we have programs next week, I'll be much better at all of this. Thanks.
Thanks, Caroline. And before we get to the meat of the night, I wanted to just thank some sponsors for the Tools exhibition. It was made possible by major support from GE. Generous support was also provided by Newell Rubbermaid, Dorit and Avi Reichenthal, and Esme Uzdan. And additional funding was provided by the August Heckscher Exhibition Fund, Facebook, the Aaron Krantz Fund, and the Smithsonian Institution funds from the Grand Challenges Consortia. And I also wanted to give a big thank you to Amanda Kesner, who has taken over this program seamlessly and has organized it for everyone. Thank you, Amanda. And of course, Caroline Payson. Just a little background on the Tools Extending Our Reach exhibition. It's a pan-Smithsonian Institution show. So it's bringing together works from 10 Smithsonian museums and research centers, including the Cooper Hewitt, as well as objects from outside lenders. There's some 175 objects in the exhibition. They span different cultures, different time periods, different materials and functions, and together represent 1.85 million years of human design. And that's starting with the earliest tool in the exhibition, which is this wonderful chopper stone from Tanzania, to this very contemporary example of almost live images of the sun. This is yesterday's sun. And this underscores, Kara and I, when we were thinking about the exhibition, we really wanted to underscore the design focus of the show. So we decided not to do it chronologically as a history of tools, but instead to really celebrate both the similarities and the differences by grouping objects according to function and purpose. And so we came up with the categories of work, measure, observe, survive, communicate, make, and toolboxes. So those who haven't seen the show, this is how we've begun loosely categorize these objects. And when Karen and I first started talking about the exhibition, we really wanted objects across as many Smithsonian museums and research centers as possible. And that means if you had to count them all, we would be looking at 137 million objects, which of course is impossible, but we still wanted to include as many as possible and also include objects representing many different scales. So in order to really present the enormous range of tools and their applications. So our first thought was something really, really big, like a satellite or an airplane. So we talked with our colleagues at Air and Space Museum, like Paul, who you'll meet in a second. But they just, some of them wouldn't fit into our freight elevator, our new freight elevator. So we chose smaller scale ones, but still, I think, very imposing when you see them. Other really large objects, like Big Bertha, who was also in the intro slide, which is the world's largest tunnel boring machine. It's currently underneath the city of Seattle. How do you bring that into a museum? We really wanted to represent it as being kind of this ultra drill, if you will. And so we have a model of it. As you can see, this is, they have a little car next to it to kind of give you a sense of scale. There's also a person here that gives it a sense of scale. And in the exhibition, we also tried to capture the actual diameter of the cutter head, which is this, by actually drawing it on the, or at least a portion of it on the wall. So it's 57.5 feet in diameter. So it was almost like having Big Bertha in the galleries. But even the scale of our own planet, I think, is becoming more and more familiar to us. Due to the many images of Earth from space that we have seen in all types of media, including this example from the cover of the Whole Earth catalog that's in the exhibition. And we are learning very quickly where our place is in this universe. And you can see the little dot at the lower left corner, that's Earth, compared to the sun of 2 days ago. But we also wanted to represent the opposite end of the spectrum. So not only things that are huge, but something that is really, really, really small, like this TIMU chip, which stands for a microsized timing and inertial measurement unit from the Microsystems Laboratory of the University of California, Irvine, which one day might replace our GPS. Or, and this is actually a tool for some of the software engineers to work on these small chips. This is actually kind of a diagram or a map of that particular chip. Or the world's first insect-scale flying robot called the RoboBee, which was conceived by a design team at the Harvard School of Engineering and Applied Sciences and the Wyss Institute to combat the depletion of honeybee colonies. So this is all to try to imitate swarming behavior. So you can see how extremely small it is, using the penny as a measurement of scale. But how do you even design on these small scales or these large scales? What kind of tools does one use to go from the micro to the, as we see in Charles and Ray Eames' Powers of 10, where you can see they go from the microscopic to the satellite view of Earth. So this is where our esteemed panel enters the discussion. So what I'm going to do, I'm asking each of them to make a 10-minute presentation introducing their own perspective on scale as it relates to their particular profession, whether it's as a curator, historian, engineer, and inventor. And then this will be followed by a Q&A with me. And then we will open it up to the audience for hopefully the last 20 minutes to half an hour. So I'm going to introduce our first speaker, Paul Ceruzzi, who is chairman of the Space History Division at the Smithsonian Institution's National Air and Space Museum in Washington, D.C. He received his BA from Yale University in 1970 and a PhD in American Studies from the University of Kansas in 1981. And prior to joining the Smithsonian, he taught history at Clemson University in South Carolina. And at the Air and Space Museum now, he's worked on several public exhibitions, most recently Time and Navigation, which covers the art and science of navigation from 18th century seafarers to the current systems of global positioning satellites. He is currently working on a major renovation of the Boeing Milestones of Flight Hall, the entrance hall to the National Air and Space Museum, which is scheduled to open the summer of 2016. He has written several books on the history of computing and aerospace technology, including Beyond the Limits, Flight Enters the Computer Age, Internet Alley, High Technology in Tyson's Corner, and most recently, Computing, A Concise History. And it's a book that's actually this small, so it's very concise. A book-length study of the social and technical history of the global positioning system is forthcoming in 2015. So please welcome Paul. Thanks.
Thank you very much, and thank you for the introduction, and welcome, and it's a great honor for me to be here. This is a very exciting opportunity for the Air and Space Museum to participate in this wonderful exhibition, which I had a great time looking through, and see if I can somehow bring my perspective to all of this, and let's see where we are. So, as she said, I'm the chairman of the Space History Division at the Air and Space Museum. I feel a little bit of the odd person out in the panel because I don't make things, but I show things to the public. We decide sort of what it is that we think the public would be interested in. And we are, as you probably know, one of the most popular museums in the world. And we think about that a lot of times. We think, well, anybody could be a curator there and you'll bring in the crowds, which may be true, I hope not, but we do work very hard to make our exhibits popular, and I've thought about, well, what is it about them? And I think it is really a matter of the scale, that it's the human scale. Now, we don't have an Airbus A380 in the museum, but we do have the nose of a 747, very popular exhibit. We also have a Concorde, and we have the original prototype for the Boeing 707 and a space shuttle. So those are things that people really, they relate to the size of it because it's a human scale. Now, you saw that bee, that robot bee, and this is another example of how small things can get. The human body really determines a lot about the scale of what we do in aerospace. You have certain needs of your size and weight and your need for air and comfort and things like that. And when you design machines, you have to design to that criteria. And of course, when you take the human body out of the equation, you can do all kinds of cool things. But I don't think our museum would be so popular if we didn't have the emphasis on the human conquest of air and space. I think it's a real human endeavor, and it's something that we never forget, even though we have a lot of technology and science and other things in that museum. I mentioned something called the Reynolds number, which is, some of you may know about. It's the property of air, and when you have a certain size of machine that you go into the air with, the air has certain properties that allow you to get off the ground. When you get small, the air feels very different. It feels like you're swimming in molasses. So it's a lot easier to do things like that at a small scale, but you can't really make a flying bumblebee at a human scale. I don't think we've ever made anything that flapping like a bird that's maybe gotten a few feet off the ground. That's about it. But practically speaking, it's just not going to happen. And it's the sort of basic laws of structural weight that you have to sort of keep in mind. With spacecraft, it's even more crazy in a way that you have these enormous vehicles that burn through thousands of gallons of fuel and oxidizer to get off the ground. It just sort of lumbers off the ground. I compare it to a Greyhound bus pulling out of Port Authority. It's sort of, and then what do you got at the end? You got this little tiny capsule that John Glenn said, you didn't get in the capsule, you put it on. He was squeezed in there. We've got it on display, and boy, I'll tell you, it is small. We went from there to the space shuttle. This is on exhibit at the Air and Space Museum. 7 passengers in cargo, about the size of a small aircraft. Very, obviously the public loves this thing, as you might imagine. It's incredibly impressive, but it's also it really pushed the state of the art for size. And I don't think and I'm not speaking as an engineer here, I don't think we're ever going to build anything this big again to go, to bring human beings into space and back again. I really think that that kind of pushed it a little bit farther than it probably had to go. We are going to build shuttles again. There are plenty of them on the drawing board, but they're going to be probably smaller. So, and there's good reasons for that from an engineering standpoint. So another issue that we deal with is, as you probably know if you've been following the space program, there's all kinds of talk about we've got to go to Mars, we've got to get beyond the moon, we've got to extend our species into the entire solar system, colonize the planets. We may be finding life on the moons of Jupiter and things like that. What are the practical issues? We don't have a Saturn V in our exhibit, although there are 3 of them in existence in Huntsville, Alabama, Florida, and Houston. But they're 360 feet tall, 6 million pounds, and what did they do? They took 2 people to the moon for a few hours, and then they came back again. That was really pushing what we could do with all of the technology and the massiveness of that vehicle. We then scaled back to the shuttle. Now there's a plan. If we're going to go back to the moon, we're going to go to Mars. This is what it's going to look like. It's a little bit taller. The Saturn V is about this tall. It's got solid boosters, which are derived from the shuttle. It's got engines, which are derived from the shuttle. It's called the Space Launch System, but it's again pushing the limits of what we can do. So why are we doing this? And of course, you have these robotic vehicles with the tremendous advances in microtechnology that can do all these things. But a couple of people have pointed out to me that if you could have gotten, you all know about the Curiosity rover, which is on Mars and doing all kinds of wonderful things. If you could have gotten a human being onto Mars, he or she could have done the same kind of science in about a week of walking around that the Curiosity rover has taken a year to do. So you want the human being. Now you've got to solve all these technical problems to get a human being there. But that's what you have to, human beings want to explore. It's in our nature. And we're going to explore one way or another. We're going to find out a way to do it. So again, this is the scale that we have. These are the thing of the very popular now CubeSats about this big that are built in college campuses. Can do all kinds of wonderful things using recycled iPhone parts and things like that. This is sort of the upper limit called Tracking and Data Relay System, which is up in geostationary orbit, which interesting story there where the early days of the space program, you had tracking stations all around the world, some of them in politically very sensitive places where people were a little nervous about Americans coming in with sophisticated electronic equipment. All of that has now been replaced by a series of satellites way up in space where you send the data up there and then down to the ground in the United States, and you don't have to worry about that. So that's a big thing. This is a little thing, but do we really want to have a whole bunch of these swarming around in low Earth orbit? I'm not so sure about that. It kind of could get a little bit polluted up there. So I'm going to conclude just really quick. You've got an iPhone upstairs, and you know all about all the things it does. Our exhibit opened at the Air and Space Museum last year that shows an inertial navigation system from a submarine. There's the gyroscopes, the accelerometers, there's the computer, there's an IBM typewriter, which is a keyboard. Those are the radios. Here it is all in the iPhone. You've got all of that. The irony of it, though, is really weird because this device was used to navigate the submarine so that it wanted to stay secret. That's what a submarine is for. And it had to poke a little antenna up every once in a while to take a fix from a satellite to fix its position. Most of the time it was completely secret. They didn't want to tell you anything about them. In fact, submarine people are the quietest people on Earth. They really just don't talk. The iPhone tells the whole world where you are all the time. whether you want to or not. They know where you are. Somebody knows where you are. And it's usually a department store or Google or somebody, but or somebody else. I don't even want to go there. But anyway, but it's the same technology. It's just shrunk a lot. So with that, I guess when you change scale, all kinds of interesting things happen. And I think I'll just leave it at that. Okay? Thank you.
Okay, our next speaker is William Goodrich, who is an Executive Vice President at MTA Capital Construction, MTACC, and the Senior Program Executive for the East Side Access, a $10.2 billion transportation infrastructure project currently under construction in New York City for the Long Island Railroad. Mr. Goodrich is a registered structural professional engineer with over 30 years in the transportation and construction industries. East Side Access is the third MTACC mega project that Mr. Goodrich has worked on, and he is a noted expert and seasoned professional with deep and extensive experience on the largest and most complex of infrastructure and building projects. Prior to being chosen to lead the East Side Access project, Mr. Goodrich was the program executive in charge of the 2nd Avenue Subway project, where he oversaw the design and construction of the $4.45 billion first phase of the project on Manhattan's Upper East Side. Welcome, Bill.
Thank you, Matilda. Let me just escape out of here. Oh, we can just advance?
Yeah.
Go back to the slide then. Okay, thank you, Matilda, for that kind introduction, and welcome everyone. I'm glad to be here tonight as part of this inaugural presentation. I'm excited about the museum reopening and having this exhibit and display as one of its first. I'm going to talk a little bit tonight about East Side Access, and that's the current project that I'm working on, and obviously one of the questions that some of you may be familiar and several of you may not be familiar with what is East Side Access. And I'm also going to talk in terms of scale, as Paul started us off on. We're going to talk about tunnel boring machines and some very large construction equipment and construction tools. But what I find fascinating about the construction industry, there's an awful lot of hand tools and an awful lot of innovation that has to go into how you use a whole variety of a scale of tools to do different things as far as trying to construct what the designer has provided to the contractor. East Side Access is one of the 3 mega projects under construction by the MTA right now. 2nd Avenue Subway is about $4.5 billion for phase 1. That's scheduled to be completed in December of 2016. The other one, a little more near term, is the 7-line extension to the west side. That's about $2.4 billion. And that actually is going to be go into revenue service the 2nd quarter of this year. So they're getting pretty close on that one. East Side Access is our largest infrastructure project. Happens to be the largest transportation infrastructure project underway today in the United States. It's the first expansion of the Long Island Railroad in over 100 years. This is a good diagram. It really shows what we're doing. Right now, as most of you know, the Long Island Railroad comes into Penn Station, and Metro North comes into Grand Central. And the primary purpose of the project is to bring Long Island Railroad into Grand Central Terminal. So we've done tunneling in the in Sunnyside Yard in Queens on the right side of the screen. We've made a connection to the 63rd Street Tunnel, which was built back in the 80s for the New York City Transit, but it was also built with a tunnel for Long Island Railroad with East Side Access in mind. So this is a project that's been in planning for decades, and incrementally we've been putting infrastructure in place for it. And then the tunneling, I'll talk about in a minute, comes down through Manhattan from 63rd Street, underneath Grand Central, down to 37th Street. And as you can see there, it's about 10.18 billion is our current budget, with a revenue service date of December 2022. This is a rendering of what's being constructed. It's about a 350,000 square foot concourse below Grand Central, and it has a new 8-track station that is beneath Grand Central, connected by high-speed escalators from the train platforms up to the concourse. We're also building new train yards and maintenance facilities in the Bronx and Queens, and new modernized ventilation and power facilities both in Queens and Manhattan. The main project benefits are shown here. If you look at the ridership coming in from Queens and Long Island, there's about 160,000 passengers per day that come into Penn Station, but their destination isn't Penn Station. Their destination is the Grand Central area, the Central Business District. So for those passengers, it'll provide a direct ride into the Grand Central area, and it'll save commuters on the order of 30 to 40 minutes per day. It's also going to support job growth in the area around Grand Central Terminal, where there's a lot of development planned. And it's going to improve our East River Tunnel capacity by over 50%, because we'll be diverting traffic from Penn Station to through the 63rd Street Tunnel below Grand Central. So some of the tools and equipment that we are used on East Side Access. Tunnel boring machines, we've used 4 tunnel boring machines that I'll talk about. This is a Selly TBM. Selly is the manufacturer. We also had a Robbins machine. This is a Hard Rock. Both of these are Hard Rock tunnel boring machines, TBMs. And this is a pretty good picture, and they're all pretty similar, where they use what we call cutter disc technology. You basically have cutter discs that actually score the rock, and it's the pressure of the cutter head on the rock that cuts the rock and grinds the rock into smaller fragments, so you then can remove it. This is the route in Manhattan. The dotted line on the right of the screen was the existing 63rd Street Tunnel that came under the East River to 2nd Avenue. What's shown in, I guess, blue is the new tunnels that were excavated. We did 8 drives in Manhattan with 2 Hard Rock TBM machines over about a 4-year period. 2 tunnels go into 4, go into 8 as they come into the terminal. You can see where the terminal is shown in red. And then we have a tail track area that goes all the way down to 37th Street under Park Avenue. And there's 4 tail tracks. So we've got the ability, we'll have the ability to store 4 trains at the rear of the station. This is a picture of one of the tunnel boring machines holing through, which is an exciting part of because you're at the end of a drive. There's an awful lot of work that's gone into getting to that point. This is a picture. Actually, if you were to go to the very south end of where we were tunneling, down to 37th Street and Park Avenue, this is the end of the TBM drive. And we had two Hard Rock TBM machines. The Robbins machine was removed by the contractor and dismantled. The Selly machine actually was backed up from this point, and the crew took a hard right turn and buried the machine in the bedrock. So we've created a time capsule down around 36th Street and Park Avenue for someone in the future to uncover quite a surprise when they excavate or drill in that area. These are the what we call soft ground tunnel boring machines that were used over in Queens, underneath the rail yard. These are designed differently. They basically have the ability to go through soft ground, and they do it under what we call a slurry mix to maintain the stability. There were 2 machines, 4 tunnels, and 4 drives were done over about a 2-year period. Heron Connect was the designer and manufacturer, German company, for these machines. And all of our tunnels are 22-foot diameter tunnels. That's the tunnel size for both the subway and the railroad. This is a diagram of this is Queens Boulevard at the bottom of the slide, and you got Northern Boulevard just to the left to kind of get you oriented. And this is the Sunnyside Yard area in Queens. So we had to build a box first to assemble the TBMs and launch them, which is shown in the lower left. And then you can see where we had the 4 tunnel drives that went out through the underneath the Sunnyside Yard, underneath the active rail lines. This is just a shot of the launch tunnels. You actually have to cast these in concrete to build a place to, like a starter. It's like a pilot hole for if you're doing trying to drill a hole. This is like a pilot hole. You got to start with just the launch area. This is the part of the machine coming in. Give you an example on 2nd Avenue Subway when we built the launch box at 96th Street. Took the contractor, they had 35 trailer loads of equipment that came in to assemble 1 TBM machine to operate on 2nd Avenue. So you can imagine the amount of time and effort by the contractor and the crew to assemble the machine. This kind of gives you a sense of the scale of the machine and the hydraulics and the electric as it's going together. You can see the men standing at the bottom here. And when it's all assembled, it's ready to go into the launch box, launch block. And as it completes its drive in Queens, it breaks into a reception pit, a receiving pit, and you can see in the foreground the mixture, typically of bentonite clay and water, which is what keeps the machine and the soil stable while we're excavating. We also have smaller machines. They're not all 22-foot diameter. We have a number of 6-foot diameter tunnels that rail yard, and one of them is pictured here on the right-hand side, and we call this micro tunneling, and these are really for utility crossings for power, signal, sewer lines, various utilities that need to cross the rail yard. So we did not have the luxury of shutting down Amtrak or Long Island Railroad for this project. We had to maintain an operating rail yard. So micro tunneling with small boring machines was utilized to cross the rail yard. This is the other end. And there's a lot of work to get these machines in and out. So this is the demobilization of the machine. A lot of construction challenges in projects such as this. I'm going to touch on some of these as I go through some of the other tools. I'll go this way. So obviously we need to modify tools and use specialized tools for different challenges. In areas where we really can't use blasting or a tunnel boring machine, we'll use what's called a road header. And it's kind of a gnarly looking machine, but these rotate and you can put them we put them inside the cavern, and if you look closely, you can see the grinding on the walls. So we'll trim the walls back to call it finer work than the tunnel boring. I mentioned before we had escalator wellways, which we have a total of 17 escalators that are going to service the new train station up to the concourse. So one of the challenges was, how do we excavate these wellways? This is what the escalator is going to look like in the future as you come up. But inside of the terminal, below the terminal, this is what it looked like when we started. We first had to remove columns and do underpinning and put in these large beams all the way across to create an opening where these wellways were going to go. And then you can see that we've started doing some rock removal here to start the wellway. Then you get into, of course, the wellway is a steep incline for the escalator. And you've got specialized equipment like the Menzie mucker that is quite a piece of equipment. It has articulating not only the boom with the excavating bucket. Each of the tires and legs of the machine can be independently operated and adjusted. So this can move up and down over rough ground, as well as up and down an inclined slope. And you can see we used a muck car here on the side on a rail, and it comes up and down on a winch system. These are some of the tools that are used in this type of construction to excavate rock. This one is kind of interesting. This is called a raised bore machine. This was down at 37th Street. We had a need to put in 3 vertical vent shafts very close together, and you can see we're near the existing Park Avenue tunnel, the Lexington Avenue subway line, and we're in close proximity to the Union League Club. So blasting was not an option for these. This is a picture of the Union League Club and our work zone out here, and you can see the drill shaft, which I'm going to explain in a minute. This diagram here, a raised bore machine, if you look over on the left, basically you start with a pilot hole and you drill down to your tunnel area that you're trying to sink your shaft to. And inside there, you then can build and assemble the raised bore portion of the machine, and then you actually excavate it from the bottom up. And gravity, of course, you drop the rock into the bottom of the tunnel to remove it. So this is what it looks like in the field. You have to assemble this in the bottom of in the tunnel, which is eventually the bottom of the shaft. So you can see the crew here, a lot of handwork, a lot of chain falls and stuff to move these heavy heads around to get them all aligned. So what it's going to look like, it looks like this when it's all assembled. And this thing then is raised by the equipment at the surface and begins to turn slowly and grind the rock and start excavating the shaft. It took about a shaft to actually excavate it. But just like painting, there's a lot of work, prep work, to get ready to paint. Some of the hand tools that I referred to, this is probably a good example here. We place an awful lot of concrete in the caverns and tunnels. You got a crew here using a vibrator. The man on the left's got a vibrator where we consolidate the concrete, we move the concrete. And of course that has to have its own motor and power, and that's what the guy on the right is holding, is the motor that operates that. And then you get into, you get these very large caverns, and you have the need to do shotcrete work, which is another concrete technique, and you got to have articulating hand booms, or man lifts rather, that get the people up high on the wall where they need to be so they can do that. The shot on the right is we move an awful lot of material, whether it be concrete, water, air, by pipe in the tunnels, and they're all this crew here is using a drill to tighten a coupling. It's all mechanical coupling for this pipe connections. A lot of work goes into placing concrete. On the left, you can see all of the through bolts and all of the braces and stuff that go into formwork that you need to put in place in order to place and build reinforced concrete walls. The worker on the right has got a hand drill that he's chipping and removing concrete. The yellow material in the background is the waterproofing. All of the tunnels are waterproofed, and as well as the cavern. And there's always a lot of drilling of temporary attachments that need to be made. This crew here is what we call lathers, and it's a little hard to see, but what they basically have in their tool belt is a spool of wire, and it's just simple steel wire, and they have cutters, and you want the wire to be able to bend but not break. It needs to be strong enough that they can tie and make mechanical connections from one piece of reinforcing steel to another. It's to hold the reinforcing steel in place until such time the concrete can be placed around that. And you know, that's all handwork with wire and ingenuity. In the rail yard, we've got challenges there because of an operating trains. We don't have a lot of room between rail lines, and oftentimes you got to do an awful lot of handwork, especially when you start excavating at the surface. And even some of the larger excavations, they're trying to uncover a large pipe, a utility pipe at the bottom of this excavation, and this ends up being handwork. You know, there's a lot of hand shoveling. They're shoveling into a skip pan, which then comes to the surface to get loaded out. So this is just a simple picture. As advanced the technology is for a lot of TBM machines and that sort of thing that I've shown, there's also an awful lot of hand digging with various types of shovels and pinch bars for various equipment in heavy construction. So, thank you.
Okay, our last speaker is Chuck Hoberman. He's an inventor, and he seamlessly fuses the disciplines of art, architecture, and engineering in his work on transformable structures. Through his products, patents, and structures, Hoberman demonstrates how objects can be foldable, retractable, or shape-shifting. He is the founder of Hoberman Associates, a multidisciplinary practice that utilizes transformable principles for a wide range of applications, including dynamic architecture, transformable stage sets, consumer products, deployable shelters, and structures for aerospace. Examples of his commission work include the transforming video screen that served as the primary stage element for the U2 360-degree World Tour in 2009 through 2011, the Hoberman Arch in Salt Lake City, installed as the centerpiece for the 2002 Winter Olympics Games, a retractable dome for the 2000 World's Fair in Hanover, Germany, and the expanding geodesic dome at the Pompidou Center in 1997. And he's also been included in some of our exhibitions here at the Cooper Hewitt, the triennial being one. So Chuck?
Thanks, Matilda. Give me 1 second. So when Matilda told me that I would be on a panel that was titled Big and Bigger, I explained to her that if I'm on a panel with Bill Goodrich talking about tunnel boring machines, maybe we should call it Small and Smaller. But we've decided between ourselves that scale is a flexible metric, and we can look at it from a few different ways. I have a design and engineering practice, Hoberman Associates, and we focus on what I call transformable design, which is basically designing objects, and they could be buildings or stage sets or pieces of artwork or toys that change size, that change shape. I'm a mechanical engineer by training, and I make a lot of prototypes. But this is really the starting point for me, something very small, something very tactile, that begins to express kind of the relationships that I'm interested in terms of shape transformation and movement. So these are just laser cut plastic linkages. Nowadays, we can also make these types of structures using 3D printing. So this, in fact, is a mechanism that's comprised of hundreds and hundreds of joints that transforms, but it's all done from a single 3D print. This is a prototype for a kind of a curtain. And then you'll see that a prototype like this shows the actual physical scale mock-up. It's for a curtain for a residence in Japan, which is about 30 feet across, being raised up. So building at scale, does it tell you that something is going to work? No, but it can tell you that something may not work. But it's a precursor to doing the kind of the testing that a mock-up like this has. We do a fair amount of architectural work for facades. This shows some manufacturing processes for a technology we call tessellate, which are transformable screens. This is done at the Zahner Company in Kansas City. And I'll show a brief video of this particular project. So it's kind of a mid-scale project for us, somewhere between architecture and art. It's 8 screens, each one about 5 feet wide by 12 feet high, of shifting layers of stainless steel that control the light coming into the space. And it's at a building called the Simon Center for Geometry and Physics. So I've had this sort of concept for transformable design for a few decades now, and it's been a company that's a little bit unusual in that it is based on more of a kind of a design concept and not on any particular sector, but we've applied it in a number of different sectors at a number of different scales, and it basically runs the gamut from kind of miniature medical instruments all the way up to architectural scales. So this would show this is actually more on the research side, but some work that I'm doing with the robotics lab up at Harvard, which is actually the same lab that did the RoboBee that Matilda referred to in the exhibit, showing a Hoberman linkage that's built out of a kind of a carbon laminate using micro machining techniques. So you can kind of get the sense of how tiny these little articulated links are. And then at the other end of the spectrum, we're part of the team that is designing the retractable roof for the new Atlanta Falcons Stadium, which I think is due to be finished in around 2017. So somehow, from a design standpoint, there is this question of, in each case, from something the size of your thumb to something the size of a football field, you're still using the same basic mechanical principles, and there is something common in terms of the system. So for this particular project for the Atlanta Falcons Stadium, we were more involved in kind of the creative concept stage, and this is a scale model that my group constructed. That's 3D printed panels that are sliding in a linear fashion to create this oculus. And then you can kind of see at scale what it will look at, and 360-degree architects created this. And it's a very unique design in that it's an aperture, but an aperture that relies on linear motion instead of rotary motion. And will be actually quite an unprecedented configuration for a retractable roof at this scale. For a project like Atlanta Falcons, we're we're just a small consultant as mechanization specialists on a very large project. But for more of typical projects for Hoberman, we do everything from design through all the way through the construction process. And this is a project which was, at the time, the largest we had done to date, which was a curtain for the Winter Olympics in Salt Lake City in 2002. And it was a kind of a curtain that was on so-called Medals Plaza, where they gave the medals out every evening. And you can see here, the size of this is about 72 feet across. These are individual panels. Each one is about 4 by 8 feet, made of extruded aluminum, connected together in a kind of a truss work. And then these were assembled in a horizontal configuration at the fabricators called Scenic Technologies, where it was tested, and then ultimately was raised in Salt Lake City at Medals Plaza. So I always remember these moments of it being raised. There's a specialized crew running 8 different chain falls that are basically being manually operated to synchronize the raising. It's freezing outside. The wind's blowing, and you're kind of like putting this thing in place, which ultimately you're told will be seen by billions of people on TV, and the thing damn well better work. Fortunately, it did. It did for the 17 nights of the Olympics. You can see it working here, and then how it operated during the actual performance, where it's integrated with lights and music and dance. I have always really loved working on these theatrical projects. They're every industry, and I worked in a number of them, have different cultures, and I always think of sort of the live entertainment industry as one where people tend to say yes a lot more than no. Architects are a little bit different, I would say. The U2 project, Atlanta Falcons notwithstanding, has been really the sort of a peak of working at scale, and we were asked by the band and by the creative team around the band to create what they said was what they wanted was a transformable video screen. So what the idea was, the tour was called 360 because it was basically theater in the round, and they had conceived of this idea of making this giant superstructure, which they called the Claw, which was a steel structure spanning about 200 feet, which is actually pretty large. And they built 3 of these, which could be set up in different stadia at different venues, and then would be different elements would be added to that. So wrapped with a kind of a tensile fabric. There was a stage that actually had these kinetic bridges that would move around so the band can move from the center out to the sort of horseshoe. The speakers themselves, which are each about like 2 stories high. And then our piece was a video screen. And the design brief for this was they had built the Claw. They knew that they wanted to have a very unique screen that somehow incorporated a kind of a Hoberman philosophy of design that would physically change its size in addition to having media on it. And so with this sort of incredible team who are, you know, aside from myself, we're all kind of legends in the rock and roll world, we started to sketch up designs and quickly came on this idea of using the Claw to support an expandable screen that would kind of extend down towards the band. The shape of it changed a little bit so that it became kind of an ellipson plan, a conical ellipse. And what you're seeing on the left, on the blue, is representing a high-resolution video, about 4,000 square feet of it, which basically acted as a funny shape, a rather conventional video screen, but then midway through the show it extended downwards. The size of the screen was about 85 feet high and about 85 feet across. The mechanical moving parts along with the electronics weighed about 30 tons. And I mention that in relation to the kind of structural analysis that was done by our partners on the job, the engineering firm Bureau Happold, where we were studying this, you know, unprecedented kinetic piece, you know, of 30 tons, which was all being basically put over Bono's head. And there was a lot of concern about, was this thing safe, was it secure? And it actually was an incredibly tense kind of a situation. It is sort of exemplified by these diagrams where, you know, we used the structural analysis tool to show magnified deflections, which means that what you're seeing is the screen, which is like a giant metal net. When the wind blows on it, its shape deflects, and then the computer would basically predict the deflected shape, but exaggerate it so that you could actually see the pattern. And I always remember the one that's sort of in the middle on the bottom, because that was basically, the wind was coming from the left, but the screen was being sucked in from the right. And there was a huge debate, did that make sense? Were we really going to see this kind of suction effect? And you know, that kind of a debate on a project like this is where you're really working with the limits of engineering knowledge. And a lot of the time, I think lay people think that if you're working with all of these great computer programs, that somehow it takes the uncertainty out of a project. And in certain ways, it actually enables more uncertainty to occur because you don't know whether in some way it's kind of a garbage in, garbage out situation. But ultimately, kind of the collective experience said, no, that did make sense. We could trust the models, and we went on. This is a movie made by our client Barco, who was the LED manufacturer of the screen being assembled. There's different of these linkages being put together with high-strength bearings, basically 96 units, each one weighing about 700 pounds. They invented this kind of robotic forklift to assemble it, although I'll say that the kind of the incredible, most incredible thing about this project is the way that they could assemble this giant screen in about 6 hours, totally based on the skills of the roadies who went along with the band. One thing I learned, you know, having attended a few of the concerts, is don't get in a roadie's way because they'll run you over, because they just don't care about anything except what they're putting together. And then the concert itself, where really it all came together, and you can see here the screen. And this shows a highly sped up version of the transformation of the screen. So again, it's a 7-story high object. It kind of just transforms in a way that really is kind of just a very, very different experience than really anything I could have imagined, although, you know, I sort of designed the thing as well. And then this shows it being kind of painted with these wonderful lights and images by Willie Williams, the band's creative director. And then so from here, I'm going to be jumping way down in scale and really something that's a little bit, it's actually a little bit more contemporary, which actually has to do with, it's a little bit off subject, but I think it does relate to scale. And also really a lot about the way tools and methods actually come together. So I'm teaching a lot more now. I'm teaching up at a few places, but at the the Harvard GSD Graduate Design School, and teaching basically build kind of similar structures to what I do. And they're building some pretty large things for using these techniques. This is a wooden expanding dome being tested, and here's kind of a different one. And so it's very interesting to kind of like say, you know, the work that I do has always been a little bit, you know, has been highly special, but we're finding ways to kind of put it in the hands of young generations of designers who are finding, you know, ways to extend it. So this gives me, you know, some hope that these ideas may be kind of extended in the future to make transformable architecture in all kinds of new ways. The last semester at Harvard, I taught a very different kind of course called Informal Robotics, and it's basically making robots not out of metal and hard machinery, but out of paper and soft gels. The idea is, can you fold and motorize a piece of paper and get it to walk across the table? And it's pretty cool stuff with very, very interesting design methods. And I'll just end with this image of this little walking platform, and it just looks like it's kind of like walking at random, but here you see it's sensing actually. And all of that is done by just a differential flexure of the paper. So it's an integrated kind of piece of this incredibly simple design concept with huge sophistication in terms of how it's actually implemented. Thanks.
So we're going to have a little bit of discussion, and then we're going to turn it over to the audience for some questions. So one of my questions has to do with kind of the process and getting from small to big, especially, Chuck, with some of your projects. What are the kinds of tools that you use to calculate getting from small to big? I mean, beside, I guess the computer is certainly important, but how do you get, if you're doing a prototype, how do you then get to that sort of final stage of a big structure?
Somewhere between the prototype and the finished structure is very often a mock-up. So it may be, the mock-up would be considered, say, typically something that's built at scale, but is not the complete structure. It's just kind of a piece of it. And that very often gives you this understanding of manufacturing processes and performance, even though it's not a full system. But you can usually use that sort of, it's like, kind of like cross-correlating and triangulating between that kind of information in the prototype and the computer analysis, et cetera, as well as the insight of the design.
And is that, Bill, in terms of how you, I mean, where do you even begin to kind of, I mean, do you do scale models? How do you begin the process of designing a tunnel? Knowing that you're going to use a tunnel boring machine somewhere along the line, but what are the steps leading up to that?
Well, I think there's several factors that kind of are your starting point. You know, obviously the geological conditions that you're dealing with are a big part of it. There's an awful lot of investigation of the soil and the ground conditions and the rock that's done by the engineers to evaluate you know, the vertical alignment of the tunnel, how much cover you need to maintain for the required factors of safety. To give you an idea, generally along 2nd Avenue, we maintain about 25 feet of rock cover from the crown of the tunnel to the top of the bedrock. And of course, building tunnels in any urban area, you've got the existing tunnels, the existing subways that you've got to either go over or under, and a lot of that dictates your alignment. But once the alignment is set, the people that manufacture the machines, based on the technical data of the rock quality, they can design the machine with the appropriate amount of force on the cutter head to excavate that rock. As I mentioned before, the idea is you want to, people have the idea that it's a high-speed drill that's grinding the rock. The cutter head, it moves actually rather slowly, and the individual discs are scoring the rock, and it's the pressure of the hydraulics of the face, total face against the rock, that's slowly grinding the rock, and so that's a lot of the initial technology that goes into the design of the machine and setting the alignment for the tunnel.
I wanted to ask Paul, because you mentioned it, but you didn't go into any detail, but if you could talk a little bit more about, I'm really interested in the future of the space shuttle, and you said now we're going to get smaller and smaller. So why is smaller better?
Well, again, you have the limits of the human body, which determine sort of a minimum volume and comfort and things like that. And I think the shuttle program, which has just ended, combined cargo and human crew. And I think we now realize that you can send up a lot of cargo in an unmanned vehicle. You don't have to, they call it man rating, go through a lot of safety issues to send up the cargo. And then you send up the people in a 7-passenger vehicle, let's say, that is small. And when you scale things down, everything gets a lot simpler geometrically. So I think that's the future. There's actually about 4 or 5 different competing designs going on for the future human access to space. You all have heard about SpaceX, which is going to have a launch very soon. There's one called the Dream Chaser, which is it looks like a mini shuttle, and that's the one that's got wings. Wings is very controversial. Lots of people like the idea of landing with like an airplane. Astronauts don't like to be fished out of the water. I don't blame them. However, you've got to carry that weight up into orbit and then back down, and you only need the wings at the final stage of the voyage. So it's a little bit of a trade-off there, but that's one of the competing designs. The other design that SpaceX is working on is to actually come back and land. If you ever watch 1950s science fiction movies, how do they land on planet? They go, they land kind of running the movie in reverse. You go back down. Well, it's a great idea. It's never really been, it's never worked until now, because you've got to carry all that fuel and you have this problem of stability. It's like balancing a baseball bat on your hand or a broomstick. However, our friend Elon Musk thinks he can do it, and he's got some great ideas about bringing the rocket back. So that way you don't need wings. You need extra fuel. But there are all kinds of competing ways of doing this. But as I said initially, they all have a certain requirement of designing around the human body and what's the optimum number. You don't want to send one person up. You want to send a crew of about 4 or 5, let's say. That's about right. We've got 6 people living in space right now on this International Space Station. Obviously, if we're going to really get serious about space exploration, we want to have hundreds of people up there. And that's going to be an interesting challenge.
Talked initially, Paul, you said that you were interested in the idea of talking about sort of scale in terms of time. which in space is actually interesting. But also, when you think of time in terms of like your projects, which can last how many years? A long time in terms of creating a tunnel. So, you know, there's those issues of, you know, time that also are important in terms of scale and how that comes to play in the whole sort of design process.
Well, the Voyager spacecraft Voyager 1 has now, as far as we can say, officially left the solar system, kind of like Elvis leaving the building. It's passed through this phase where the solar pressure is now balanced by interstellar pressures, and we believe that it has crossed that threshold. Now, that vehicle was launched in the 1970s. So many of the scientists who worked on that are obviously, some of them passed away, they're retired, they're old, they're still excited if they're still involved, and it's been a lifetime for them.
So it's about on the scale of Second Avenue access.
About that. Yeah, I guess you could say that. And then what I didn't mention is that it takes hours and hours for those signals to come back to Earth, days even, traveling at the speed of light. So this is another thing that bothers me about Star Trek or Star Wars movies, is that you're talking to people. It doesn't work that way, sorry. There's a tremendous delay, even 3 seconds to the moon, which meant that when they landed on the moon in the 1960s, they couldn't rely on Houston. They had to be on their own because that 3-second delay was too much. And Mars is, 10 minutes. So 10 minutes is a long, long time if you're driving. Imagine you're driving a car down Second Avenue or Fifth Avenue, and you drive, and then 10 minutes later you find out, there's something in the way. Better turn left. Okay, you turn left, wait another 10 minutes. So it does take a while. That's why I keep saying that we got to get a human being up there somehow. It's not going to be easy, but I think we do.
So before I turn it over to the audience, I want to know, what is your most important tool? If you had to choose one tool, what is your most important one that you use in your job? And don't all say the same thing.
I guess I can start. I would say the most important tool for the MTA and the common tool in these mega projects is really the material, the primary material we're using, and that is concrete, and it's the variations of how you use concrete to do different things. And it's a combination of materials and tools, but you can use concrete by changing how much sand is in it and removing the rock aggregate. You can do temporary things where you spray it for temporary support, and then of course you get into your larger mixes where you're pouring slabs and walls, building heavy floors and stuff, and how to deliver concrete, and get it from the surface down deep into these caverns and down these tunnels for hundreds of feet. It requires some innovation in and of itself just to deliver the concrete from where you want the finished product, from where you have the opportunity to park concrete trucks and utilize concrete pumps. So I think all of the tools involved with the design of concrete and the different types of concrete, as well as the delivery of concrete, is probably our primary tool.
You probably gave me this question in advance, so I don't know why I should be stumped. I guess I would. It's hard to come up with a tool as an external piece. It probably has to do with, I would say, more the methods, meaning the people involved with how. I mean, I'm in kind of an innovation game where really, partly because of my interest, but also because at a certain point I had committed to inventing and making new stuff, and so I more or less, when you make new things, you're really just reliant on your brain and your the people around you and the sort of ability to engineer and make this stuff.
Collaboration.
It has to do with collaboration. It has to do with harnessing the right people and the right mindset to collaborate and bringing a few different disciplines together. I'd say that's much more important than any single, physical or virtual tool, as important as those are.
I would say, again, I feel like the odd person out here in that I'm a museum curator, but I started out with reliance on typical academic tools of libraries, research, and archives and things like that, and now I find myself a very heavy user of the internet. But it's obviously we all have the internet, but you have to learn sort of how to extract the information you need out of it. But when you can do that, it's just an incredible resource. And I do use it a lot. We're working on a new exhibit to redo the central hall of the Air and Space Museum, where literally millions of people are coming in every year, and we're using the internet for the research and the photography and all of that. I want to tell a little story because this you mentioned how you have to be careful about existing infrastructure when you're tunneling. And we have a much more modest tunnel in the Washington area, the Silver Line, the Metro, which goes underneath a place called Tyson's Corner. Not too many people realize that the internet is, a big chunk of the internet goes through Tyson's Corner, Virginia. It was one of the places where it really began. And you've heard these stories about the internet having this redundancy and robustness about it has multiple pathways in case something breaks, it goes another way, and they talk about its military origins in the Cold War and so forth. Well, it turns out that they drew these logical diagrams of the internet that showed these redundant pathways separated, but the reality was when they came to build a new backbone, they said, oh, here's a trench right here, let's put the cable right in there. So you had all this redundancy basically in one trench. And sure enough, somebody with a tunneling machine or a backhoe comes through, bingo, out goes all the all the infrastructure fast, and they realize, hey, wait a minute, there's no redundancy after. So it was a funny, I think it's funny, but maybe it wasn't funny at the time, that they had to learn that lesson when they were digging this tunnel underneath Tyson's Corner, Virginia. A very short tunnel, by the way, but they learned a lesson.
Important one. Okay, I'd like to turn it over to you if you have questions. So what we're going to do is we have Maria and Amanda will be, okay, just you, okay. So if you could speak in the microphone, there's one way in the back.
Hi, thank you so much for sharing these stories. It's fascinating. One of the questions I had really, humans are not great at really understanding scale, and so there's oftentimes things that we think will work at one scale that don't work, or that, that's what was amazing to see some of those, the diagram and how the transformations of some of the Hoberman, that work. But do you have any stories about how things that you thought would work at one scale that didn't work, or that there was a consequence that wasn't anticipated, and then how that was solved?
Wow, these are sensitive questions. Yeah, absolutely. Earlier in my career, where I had a sort of a misplaced confidence that anything I thought of would be, if I could imagine it, it would work. I built I was commissioned to build a large exhibit, about 50 feet, expanding from about 13 feet to 50 feet, for the California Science Center in Los Angeles. And I walked in with I knew basically my expanding structures like the sphere, I could build in other shapes, and I thought there's a very interesting shape you can make with a soap bubble solution. If you dip a curved piece of wire in, you get this kind of curvy saddle-like shape. And I walked into my client and dipped the wire in and showed them the shape and said, I want to build this as a 50-foot high expanding sculpture. And then, much to my detriment, they said, sure, let's go ahead and do that. I built a scale model, and it worked great. And I built the full-scale one. The thing was, with the resources I had, it was too big to kind of build and test in my own facility, which meant that I was doing it effectively on a construction site. And we hung the thing, and we turned the motor on and nothing happened. But I mean, ultimately it was resolved through kind of a lot of, sweat and elbow grease and modifications to the system. And looking back on it, the thing that I always ask is, would I have been better served by not having proposed this crazy thing at an outrageous scale, and all the lessons that I learned from it would not have been learned. And that's something that still is a question, that I have today. I couldn't really answer it. But I wouldn't do it again.
I actually have a kind of a war story as well I'll share. And this goes back to Second Avenue Subway, and I remember the date. It was August 21st, and I believe it was 2012. But we did thousands of blasts for the caverns and tunnels, Second Avenue, and they were all done, and my whole team did them safely. But on August 21st, 2012, we did have one get away from us, and this was at I believe it was 69th Street and Second Avenue, if I remember correctly, and it was a similar situation to what I showed here, where we had a escalator wellway that we were constructing from the surface down towards the cavern. And the contractor was doing the initial blast at the top of the escalator wellway. Well, they had done all the excavation, all the blasting in that area vertically, and everything went off according to plan. Everything was well under control. Well, no one really took into account the new orientation that the drilling for this initial blast was on an incline, and the resultant blast was going to be on an angle from that wellway. And some of you that are local here probably remember the pictures in the paper where there was a significant plume of blast and dirt and debris that came up and was all over the street. And I remember the fire chief, and I always questioned the fire chief that was in charge of the explosives unit, because he had us always stop traffic a block away from where we were blasting. It didn't matter how deep we were. He always had us stop traffic, both foot traffic and vehicle traffic, a block away. And I thank my lucky stars that day that he had that requirement, because no one got hurt, which was the good news. There was some windows that were broken across the street in one of the buildings, which were easily repaired. We had cleanup on the street to do, but all in all, but that changed our procedures and our process as far as how we approach some of our blasting in some of the atypical areas.
Thank you. This is a question for Mr. Hoberman. Any of the transformative structures are or could be applied to space exploration?
I should let Paul give his opinion. I have done some work for the Space Agency and for the Naval Research Laboratories, which is also a satellite maker. So they're very interested in deployable structures. I've never actually flown one of any of the particular structures that I make, but expandable structures in space have an inherent logic precisely for the reasons you've been mentioning, which is that you want to have the most concentrated kind of payload on the ground, and then sometimes you want big structures. I don't know if you have any.
No, I agree. Yeah.
Well,
Great idea. Yeah.
I agree. Great idea.
I'm really enjoying this. Thank you very much. But I'm struck by the fact that all of you are working with tools that really integrate with three-dimensional space and three-dimensional thinking. And I'm wondering if any of you has an opinion about this next generation who has a very different attachment to three-dimensional space and mostly understands it through a screen-based kind of module. And if you have any thoughts about education or about the how this may impact the kind of innovation that all of you are engaged in the future.
I'll just respond briefly. I think I was more, it's been a concern of mine because my career grew up with computers, but they were not, the capabilities were basically, you use them as a programming tool for very specialized tasks, so you weren't able to kind of interact with them so fluidly, and it wasn't an alternative to three-dimensional space. And I was kind of pessimistic for a period of time that maybe we were really losing that. But I think actually there's an interesting counter-trend now where, you know, the maker movement and 3D printing and DIY and all of that is almost kind of a renaissance of physical making as enabled by digital tools. And maybe in some ways, you know, the solution is kind of, the problem is kind of being solved from the same source, that the, you know, the solution to the problem are coming from that same source.
As far as infrastructure and actually what's refreshing to see is some of the young engineers that are coming out of school now who have certainly have a lot more computer expertise with analysis and design, and they've grown up with the tools of 3D printing and CAD modeling. So what I'm seeing in our projects, we've got a great team on Eastside Access who is doing BIM modeling, building information modeling, and they are doing 3D printing. As we're looking at design drawings, and they're putting it into a 3D model, and they're actually various elements of the structures that we're getting ready to build, and they're producing a 3D model through 3D printing that we can use as a tool to talk with the contractors, the other engineers, the designers to plan the work, and it's been invaluable to the whole team, and it's really the new generation of engineers and designers that are bringing that expertise to the team.
Near the end now of this panel talk, I was hoping we might get back to the original image of Big Bertha. I am a docent here and anticipating doing lecture tours of the tools exhibition, and we feature Big Bertha, 57 plus feet wide, is the largest tunnel boring machine. And we also feature it as dual functioning. That is, that it not only bores tunnels, but lays tiles on the walls. And we have also just learned that in 2013 it hit an impediment and is no longer operational. So can you speak to that a bit? I know it's Canadian, so I don't know how familiar you are, but I'd like to hear from you.
Yeah, the tunneling industry is a relatively small industry, so when something goes wrong, everybody knows about it. Yeah, the Big Bertha is the largest TBM at 57.5 feet in diameter. It got about 1,000 feet into its run of 9,000 feet for the Alaskan Way Viaduct in Seattle. And it did hit a 8-inch diameter steel pipe that was vertically in the ground. And as big and as massive as these machines are, they're designed to cut and grind rock and cut and remove soil. They're not designed to cut steel. And steel is one of the worst things that you could contact. You can hit timber piles, it will grind through timber piles. But when you get to, and even concrete, it'll grind through concrete. But once you get to steel, it's problematic. The main bearing failed on that machine when they hit it in December 2013. Of course, the machine, I think, is about 50 to 60 feet below the street. they had no way, they knew they had a main bearing failure and a failure on the seal, and now they're faced with how do we change the cutter head and change the main bearing. So they basically had backed up the machine slightly, and they're sinking a shaft. For a year plus now, they've been sinking a shaft in the middle of the street and excavating down to the front of the TBM machine. Once they get to that point, they then will be able to put men and equipment in the shaft at the front of the machine, and they can disassemble the damaged portion of the cutter head, remove the main bearing. With cranes, they'll lower in the new replacement parts, reassemble everything, and then they can go back to work. But that's going to represent probably about a year and a half delay in total on that contract. Well, actually, I believe right now, as they're excavating down the shaft, they're removing the steel pipes, as they encounter them, because apparently there's more than one.
I think we have time for one more question.
Thank you. This is for Mr. Hoberman. I was wondering what, in the early part of your career, what inspired you to, go with these geometric shapes from, change their size, and what's now in your career now, currently, what are you looking for inspiration as far as, things you have not done and what could be? And also, are you involved at all with the new U2 tour coming up?
Last one is straightforward. No, I'm not. I'm not involved with the new U2 tour. Inspiration. My background is originally as a artist, sculptor, and then went on to go to study mechanical engineering. So the combination of art and science has always been really the hallmark of what I was interested in and still am. The theme of transformation, it's a little bit hard to place. I mean, I had a mechanism specialty when I'd studied engineering. I was fascinated by movement and basically was working at a small robotics firm and thought maybe it would be fun in my spare time, and I had enough energy that spare time could be in the middle of the night if necessary to make some origami pop-up structures. And kind of basically started knocking on a door, and I went through it and sort of never came back. I mean, it really just had its own creative logic. In terms of what inspires me now, it's at this point, it's really very much about collaborative opportunities. When I started my career, I felt kind of like I was in a bubble, making my own way, in a way, not exactly in isolation, but without really peers who are interested in the same thing. It doesn't feel like that now. It seems that the concept of transformable design has kind of spilled over. It's just become, the lecturers of architects, of engineers. Right now I work in terms of my academic research with scientists and biologists, people making DNA structures, and you can have these fascinating conversations about whether, how these principles of transformation, which I've sort of interpreted as a mechanical function, how they may relate to a systems level thinking, and that in fact you can find all of these analogies of how this occurs in nature as well. So I've always been inspired by nature, but now I have the opportunity to work with the people who really, go to a deeper level with it.
All right. Well, thank you, Paul, Chuck, and Bill, very much for your participation in this panel. Let's give them a round of applause. And thank you all for coming. And just be sure you log onto our website so you can find we'll have lots of other programs offered. So thank you for coming.